Testing, testing. Okay, today's lecture is a continuation of the complex arithmetic chapter lecture that we had last time. And I'd like to just start again with the Euler formula and the interpretation of complex numbers as a scaling and a rotation vector. So today we're going to actually look at some of the one of the very nice applications of this to computer graphics in 2 dimensions and 3 dimensions. So we can begin that in the following. So if you remember, a complex number can be written in Cartesian or polar form. So if we have a axis here with a point xy, so this is the standard Cartesian, and this is the distance r. So r is equal to x squared plus y squared, and there's an angle theta. And if you look at tangent of theta, is y over x. This distance is the y distance, and this distance is the x distance. Then theta is the arctangent of y over x. So these give a way to go between xy and r and theta. And we can write z equals x plus iy as r e to the I theta. And this follows because of the Euler formula, which you're all familiar with, namely e to the I theta equals cosine theta plus I sine theta. And there are various ways of seeing how this works, this main identity here. You can see this through Taylor series or just by unique solution of the differential equation. So r e to the I theta is therefore r cosine theta plus I r sine theta. And if you look at this as x plus iy, you quickly see that this term is x and this term is y, and in fact x is r cosine theta and y is r sine theta. Okay. So in polar form, r is the magnitude and theta is the rotation. Now this is important because if I actually take a complex vector z and I want to rotate it through 5 degrees counterclockwise, how would I do that? And so I have a vector z that's already a certain angle theta, and I want to rotate it to another angle phi. Now we can do that just by multiplication. Multiplication by a complex number is nothing but a rotation and a scaling in the 2-dimensional plane, R2. So I would take v and multiply it by e to the I phi. Or we know that's r e to the I theta, e to the I phi, which is r, of course, e to the I theta plus phi. So we're just rotating the magnitude, if you will, r, through an angle theta and then subsequently through an angle phi. If you use the Euler formula on this, this is r cosine theta plus phi plus I r sine theta plus phi. Now, excuse me, let's correct that a little bit. Theta plus phi there. So this is a new x prime plus I y prime, and you can find the new coordinates of x prime, y prime in terms of the old coordinates x, y, just by expansion. Because if I take this is r, and then using the cosine of the sum of two angles, this is cosine theta, cosine phi, minus sine theta, sine phi, plus I times r, then the sine of the sum is sine theta, cosine phi, plus cosine theta, sine phi. Now if we look at this is of course separating it out. This is r cosine theta times cosine phi minus r sine theta times sine of phi plus the imaginary number I times r sine theta cosine phi plus r cosine theta sine phi. Okay, now what does that buy us? Well, remember, r sine and r cosine are my original x values. So this r cosine is x, r sine is y, and then plus I, r sine is y, plus x, r cosine theta is x sine phi. So this is your rotation here. So x prime is equal to x cosine phi minus y sine phi, and y prime is y, well, let's write this as x first so I can write as a matrix, x sine phi plus y cosine phi. Now you can actually write that as a two-dimensional matrix times x, y, and this is x prime, y prime. So this is what? Cosine phi minus sine phi, sine phi, cosine. Okay, so I'm going to start at that point. This is my two-dimensional. If I rotate to an angle phi, I can accomplish it by a two-dimensional vector, cosine phi minus sine, sine plus cosine. Now this, remember, is a pure rotation. There's no multiplication here. If I had to stretch it uniformly, I would multiply this whole thing by a constant r. Now notice something about this matrix, which we'll call R, the rotation matrix. We got this just from trigonometric identities or the properties of the complex variable. First of all, the rotation has determinant 1, because the determinant is cosine squared minus negative sine squared. Also, if I look at the transpose, which is what? Plus sign here, and a minus sign here, and then a plus cosine. That's equal to R inverse. Because if you multiply R times R transpose, I get the identity. So this is an orthonormal matrix, as you might guess. So what this means is that if I take any vector x and I multiply it by a rotation vector and then look at the size of it, it's the same size as my original vector. So it's length preserving. Now that's what you expect the pure rotation to do, right? Because if you have any vector and you rotate it, you're not changing its length. So these two vectors have to have the same length, so this has to be an orthonormal matrix. Another way of seeing that is if you look at the inner product between x prime and x prime, which is Rx dotted in with Rx, this is x R transpose Rx, and if this is equal to the length of x, of course that says that this matrix has to be the identity. Okay, so going back, if we take a point in the plane, convert it into a complex number, and then multiply it by another complex number, if I have a good way to do complex arithmetic, I don't have to mess with these rotation signs and cosines. I just immediately calculate the result. So this is a fast way to do 2D rotations. I take my number, xy, I formulate a complex number, x plus iy. I then take another complex number, z prime, is a rotation and scaling. Then z prime times z equals the result. So you don't have to actually calculate necessarily the theta's and the angles and stuff, as long as you have a z that corresponds to a given rotation and scaling, r e to the I theta. So that's x prime plus iy prime. And then you can do it by means of a rotation vector, or you can do it by means of just complex arithmetic. Now, if you have the ability to do complex arithmetic in the hardware, so if the complex arithmetic can be done as a hardware multiplication, this can be very fast. In the hardware, this implies it's fast. Typically, a 2 gigahertz Pentium machine runs at about 1.2 gigaflops. So a 2 gigahertz Pentium 4 is approximately 1.2 to 1.5 gigaflops. That means 1 gigaflop is 1.2 times 10 to the 9th floating point operations. And that is a lot of matrix multiplications or 3D rotations. Specialized graphics cards can even get up into the teraflop range. So the graphics card, if it has it in hardware, can do teraflops. I mean, that's a million times a million flops. Of course, these kind of graphics cards are a little pricey, maybe $300 a pop rather than $80 or something. Okay. So let's go back to our lecture here. The quaternions are essentially a 4-dimensional extension of the complex numbers. The extension. So it's essentially W, X, Y, and Z, or you can write this as W times some vector U, where U is X, Y, and Z. And the quaternions have a extension like the following. So you can write this as W plus IX plus J Y plus KZ, where I squared is minus 1. So these are like roots of square root of minus 1. And with the properties that we illustrated in the previous lecture, which came from here. Somewhere down there. Okay, so A1 plus A2I plus A3J plus A4K, and then you have the conjugate, and then you have all these rules for matrix multiplication. But what I'd like to do today is just show you a couple applications of the quaternions to do rotations in 3 dimensions. Okay. So quaternions are related to a 3x3 rotation. Now I should mention that there is a concept of, well, you can rotate about, in 3D, about an axis. So suppose we were in 3 dimensions, and here is X and Y and Z. So this is my right-handed coordinate system. If I extend X and Y into X and Y and 1, I can write the rotation in 3 dimensions about Z as cosine theta minus sine theta, cosine theta, 0, 0, 1. Because if I multiply x, y, 1 by this matrix, I will get a new number, x prime, y prime, and then the last one is 0 times x, 0 times y plus 1. These are called homogeneous coordinates. So this corresponds to a rotation in the x around the z plane. You can also rotate around the y and the x. If you look at the other matrices, you could have 1, and then you could have cosine theta minus sine theta, sine theta, cosine theta, 0, 0, 0, 0. This is rotation about one of the other axes. So now that, I guess, actually should be down here somewhere. Okay, so if we rotate go down here to where we have Eulerian angles. Which should be on another. Here's a list of preprints which are quite useful. So if we look under Euler angles, this is one way of approaching rotations in 3 dimensions. Okay, so move this here. Okay, so this, they use a slightly different notation here. If we have this matrix here, 1 cosine theta and minus sine theta, this is rotation about the x-axis here. This, if the 1 is in the center position, this is rotation about the y-axis. And this one I wrote down here is rotation about the z-axis. Now, obviously, you can combine them. So this one is rotation about x-axis. And then there's one final one, cosine theta, 0, minus sine theta, 0, 1, 0, sine theta, 0, cosine theta, is rotation about the y-axis. Now, you can get any rotation in 3 dimensions by a suitable combination of a rotation around x, rotation around y, rotation around z, then a scaling and a translation. So you have any operation in 3 dimensions. You can first rotate about the x-axis. You can then rotate about the y-axis. You can then rotate about the z-axis. And then you can scale. And then you can translate. So you actually have 5 matrices here that you have to worry about. And if you take your vector in R3, you multiply them right to left. So that means that you apply them essentially outside in. Because remember, if you take your vector x, m1 times x is the action of rotating about the x-axis. You then have to take that result and hit it with m2. So if you're going to calculate this matrix, you have to make sure that it goes right to left rather than left to right. So it's applied right to left. Now we'll get you, if you take a solid body and rigidly rotate it, scale it, and then translate it, you can get any kind of 3-dimensional. Now there are other ones that are shearing and things like this. Now we've talked about these 3 matrices. Let me show you the scaling matrix. If I take the following matrix, say, and multiply constant 1, constant 2, constant 3, 1, and I multiply it by any x, y, z, 1, what does that give me? Well, it's k1 times x, k2 times y, k3 times z, followed by 1. The 1 is just in there as like it's a scaling to make it homogeneous. So this is a scaling matrix. Let's see, if it's a diagonal matrix with constants here, this is scaling. So rotation has to do with whether you have a cosine and sine in this corner here. And scaling is if you have a diagonal matrix in that upper 3 by 3. Now, how do you do translation? Well, translation is very simple also. If you take 1, 0, 0, A, 0, 1, 0, B, 0, 0, 1, C, 0, 0, 0, 1. If I multiply that by x, y, z, 1, what do I get? This is x times 1 plus 0 plus 0 plus A. So it's translation by A. And this is Y plus B, Z plus C, followed by 1. So the translation matrix has numbers in this column. The scaling matrix is a diagonal in the upper 3 by 3, and then the rotation ones are here. Now, if I take any 4 by 4 matrix, where you have, say, A11, A12, A13, A14, etc., A23, A24, etc., all the way down to A41 to A44, X, Y, Z, 1. Actually, to make this last one kind of work out right, we should probably make this last row not, clean it up here. We should make that last row 0, 0, 0, 1. And then you can see that A31, A32, A33, A34. You can see that this matrix right here has to do with rotations and scaling, and this is translation. Now you can actually define components down here, and they have to do with perspective and foreshortening and whether things are sheared. Now, this whole analysis of the 4 by 4 rotation matrix is conveniently summarized in the following document. And I downloaded it to have a local copy. If you go to the last website, it's the OpenGL guide. This is a 616-page guide to OpenGL, but what I'm interested in is at the very end, homogeneous coordinates and transformation matrices, so it's Appendix F. Let's see, I don't know how to get all of that. Okay, so homogeneous coordinates are, I don't know if you can read this, but let me bump it up a little bit. Okay, so homogeneous coordinates are where you take x, y, z, and w, and you divide essentially by w. So you get it to be normalized to x, y, z, and 1. In 2 dimensions, it can be x, y is equal 0 and 1. So if the w is non-zero, this last component of the vector, that corresponds to a 3-dimensional point, x over w, y over w, z over w. If w is 0, it becomes a point at infinity, because it goes to this following argument here. Now, when you transform the matrix, here we go, you can see that here is this is actually a OpenGL call. What it does is it takes the 3 numbers x, y, and z, and puts them in the last column of this matrix, so that when you multiply your x, y, z, 1 homogeneous coordinates, x is translated by x, the y coordinate is translated by y, and the z coordinate is translated by z. And the last row is this. Now, what's the inverse of that? Well, if you're going to translate to the right by plus x, the inverse is translate to left by minus x, so you can verify that this is the translation. So translation is just putting 3 numbers in the last column. Scaling is just multiplying the principal diagonal in the upper left by x, y, and z, and of course the inverse is 1 over x, 1 over y, 1 over z. The rotation depends on this matrix here, which is a sort of a complicated 3-dimensional orthonormal matrix. But here it is. If you rotate alpha about the x-axis, you're putting this little 2x2 rotation matrix in the middle. If you're going to rotate by alpha in the y, that's this, and then finally the z. Now, in case you were wondering what all some of the other things were, there's a perspective where you can multiply your points by this, and that's the inverse. And that gives you a sort of a trapezoidal perspective, and then this gives you an orthographic perspective. Now, I should point out where you get those from is it's a fundamental problem in three-dimensional computer graphics is you take a three-dimensional object, this blob here, and what you want to do is you want to project a picture of that blob onto what your eye sees. Now what your eye sees is, so here's your eyeball. Your eye sees, look, that was not good. I want this. I'll use yellow. Your eye sees an image that's bounded here, and on this screen there is a representation of that blob. So when you look at that, think of this as your computer screen. And you have x and y coordinates on your computer screen. Now usually 0, 0 is in the upper left, x goes to the right and y goes down. So there's a width and a height, so there's screen coordinates. And then there's a world coordinate in this x, y, and z. Now, obviously there are problems. What you really are viewing is a cross-section of this projected down to your computer screen. But you cannot actually see a three-dimensional image. All you see is the projection of this three-dimensional image down onto the screen. And that's done by these orthographic and perspective projections. And these are 2 standard projections. Now, sometimes these are also called camera models. Now, if you're infinitely far away, this is a perspective model. There's an orthographic model which differs very slightly in the following sense, that instead of, see if I can copy this blob. Let's see, where did it go? Oops, that wasn't really that. Oops. That was not so good. Who knows if I can get that back there. I guess I don't even need that one. Well, I'll just draw another blob. It's easier. If I draw another blob and I look at what this looks like, there's another perspective that just projects it as straight lines. So essentially you get a straight line through here and a straight line through there, and you get a perspective on this. Now, the only this is called the orthographic perspective. So this is orthographic. It's like a point at infinity. It's like your eyeball is infinitely far away, so the lines are basically straight, so it just projects a flat image onto here. There's no kind of perspective. So you would see this, for example, if I were to draw a cube in a sort of a perspective, you might have something that looks like this, and then there would be one of these deals here. So that's how the cube would look for somebody who was at this point. But if I were just to draw a standard cube with exactly, I mean, this is essentially looking at it infinitely far away, but without any kind of diminishing in size. So there's no sort of convergent point here. You don't see this foreshortening. So this is sort of that point at infinity. Now, all of these come from matrices that we are, so there's appendix F, right? Okay, oh good. One more. Yeah, so rotations, perspective, yeah. So one of the things that basically, and this is computer graphics, if you will, 101, the essence of computer graphics is the following. You take a system of points that describes some object. So suppose you have an object here. And then essentially you take pieces of the object surface and you have like a little rectangular patch here. So let me just fill that in. So you have a patch with 4 points. And it needn't be a trapezoid or anything. So this is, say, x1, y1, z1, x2, etc., x4, y4, z4. Now, what do you want to do if you want to look at this thing in a rotated system? And this really is there's no surface on here. This is just a wireframe. It's just a collection of connected points. If you want to do a rotation of the entire object, you just look at R, and you multiply it by all of these vectors. And then there's also a 1 in there. So you look at these, and you come up with new points, xi prime, yi prime, zi prime 1. So these are your rotated points. So as long as you're not worried about things like applying a surface or a texture map or lighting or other things. If you're just rotating a mesh around, a connected skeleton, sort of like a Tinker Toy mesh, you just take each of these points and rotate it around. And because this is continuous, all of these points are still connected after you rotate them. And if your computer is very fast, you can take a bazillion of these guys, n points, where n can be very large. You can multiply them essentially simultaneously, if your computer is good enough, and you can essentially recompute every point on this in a new perspective with a new rotation, new scaling, new translation. Now, after you've rotated them, so step one is you essentially have to define your object. And that, in this case, would be a surface or a set of points. You then rotate, translate, scale, etc. Now you have a whole other set of points, and now you have to render it. Now this up to here involves these complex variables and quaternions. The rendering does not. Because what you have to do is you have to put a surface on it. And what that might mean is just map a bitmap onto this quadrilateral as a texture. For example, a texture. Then it gets sort of tricky. You have to remove any hidden surfaces. In other words, things that are in front are blocking things that are in the back, so you don't want to draw the things that are in the back. So you have things like hidden line removal, hidden surface removal. And actually that should be done before you render it, I guess. And then you apply your lighting. Now, what a lighting does is just take your surface, and it has like a lamp or something here, and say a lamp here, and you have your blob here, and then it'll cast a shadow, say over here, and this will cast a shadow over there. And it'll apply surfaces, etc. So the trick is, of course, to get a model, find the points on the surface, store them as a collection of points in some connected way so that the surface basically looks like a bunch of patches. You rotate and you move that object inside the visible universe of your computer world just by multiplying it by this translation and rotation matrix. You then, through a complicated algorithm that we won't talk about, remove any surface that's not visible. You then render it, putting textures on that surfaces and apply lighting. Now, if you're really good at this, if your computer is really fast, you can do this at like 100 frames per second. What that means is you can move the world, apply the hidden line removal, texture mapping, and lighting 100 times per second for a very complicated object. Now, if you've ever seen any computer-generated movies, like what was it, Final Fantasy 10, 9, 11?
We have a movie called Final Fantasy.
Yeah, it was the one.
Video game, the last one was what?
What was the movie, though? It was Final Fantasy, the movie.
But it had, like, I think it had small computer-generated movies.
Right, all the games for Final Fantasy have essentially CGI, computer graphics videos in the games, but the movie was rendered essentially this way. Every person in that movie was composed of a set of polygons, which they then moved, and of course they have even more complicated things because these are not rigid body rotations. When you have people, they have arms and clothing and all kinds of stuff. So they're very complicated dynamics, but essentially it's the same process. You get a collection of polygons, you just rotate that whole mess of polygons in the world, You then say, okay, which ones are visible, put their surface on, apply the lighting, and then render it. Now, if you really want to do fancy stuff, you'll do things like ray tracing and stuff because, for example, when you have two objects lit up, there's some indirect lighting that bounces off one object onto another, which makes it more realistic. And then you can, there's something called radiosity, so that whenever you have things which are hot, they kind of provide a glow and things like that. And there's, who knows what other effects there are. So all these virtual worlds essentially are built up of 2D and 3D rotations, which come from complex variables. So Cauchy and Euler and Gauss and these guys certainly didn't realize what all their mathematics was doing here. Now, remember there was a controversy about why use quaternions whenever matrices are just as good. This guy has a whole technical report on operational counts. Oops. Okay, so this technical report here talks about, technical issues related to, well, so this technical report talks about the difference of representing rotations by matrices versus complex numbers versus what we talked about, quaternions. So if you go all the way to the end, if you calculate the operation count for multiple repeated n vectors, the rotation matrix takes essentially asymptotically 9n, axis angle, etc., and the quaternion takes an initial 12 and then 9n. Now, if you don't calculate the angles and stuff, that can speed up. But certainly it is asymptotically the same order as the rotation matrix. But if you have software that will multiply quaternions more or less natively, rather than matrices which may have to be done term by term, you can do it a little more efficiently. Again, this came from this library of preprints from Magic Software. Now, Magic Software is if you look at the home page, it's a company essentially that is a support group for computer graphics. So they were formed in 1991 to provide support for the technical news group, computer graphics algorithms. And so they have just tons and tons of source code, etc., 2D, 3D source, basic objects, all that kind of stuff. Now there's a whole bunch of PDF files that were written by this one guy, Dave Everly, no relation to a student, Dave Everly, who does graphics, that was a student of mine. But you can look at all these things. For example, principal curvature PDF. There's a PDF file on how to calculate principal curvatures for a surface. Now, we've talked a little bit about this in the algorithms, but have not really gone to this much extent here. So this is quadratic forms and implicit surface curvatures. Okay, so I give that to you as a good reference. Also, here's a nice little example using quaternions. So this is a Java applet that uses the quaternion algorithms to do all its rotations in 3 dimensions. So it's a Java applet, which should be firing up any minute. And this, if you just drag it and rotate it, you can see that If you look at these things here, X, Y, and Z, these are the real-time rotations. So this is a little wire mesh model. All it's doing is moving points around in 3 dimensions and rendering it. Now you can also independently move the scale X or scale Y. And there's a number of other renderings here. Now it actually has Java applets to do these things. So here's a Java applet that actually rendered a fairly complicated 3D rendering, which is, see, let it load here. So what it is essentially a piece of almost like a video game. He's got particle systems for rain, so if you hit R, I'm not sure exactly what it's doing here. F toggles between the different kinds of fog. It's one kind of fog and another kind of fog. You can increase the resolution. Now, and I guess actually this, since I moved it with my mouse, it actually is rendering on the fly, which is pretty cool in the Java applet. And you can show the W shows the actual triangles that are used to generate the surface. That's pretty cool. You can do a lot in Java. There's also a whole set of online computer graphics notes if you're interested in from the computer science department at UC Davis. And these talk about the basics like coordinate systems, vector spaces, linear spaces, etc., planes, frames, transformations. Transformations here talks a little bit about what we did today. So translation is this right here. Now, one comment here, they multiply the points on the left so they multiply the vector on the left as a row vector rather than multiply the vector on the right as a column vector. So this ABC in my notation would be written down the right column. So that's a translation. So this actually talks about camera transformations down here. And that's just a more general three-dimensional rotation here. And it has to do with where your cutting planes are and your clipping planes and your far plane and your near plane and all this kind of stuff. So it just generates a 4x4 matrix. The nice thing is that all your camera angles, everything in here is encoded in a 4-dimensional matrix, and it's very easy in an algorithm to multiply 4x4 matrix times a 4 vector. Now sharing is the one thing we didn't talk about, because those are the off-diagonal terms here, A and B. Okay, so I think we've gone through pretty much, if you want the definitive source on the OpenGL, that's GL is the Silicon graphics language, which is copyrighted. OpenGL is an open source version of that, which is essentially equivalent. Everything is built on OpenGL on the very simple 3D graphics and 2D graphics primitives, which are all accomplished by 3D and 4D matrices, which can be interpreted in terms of complex numbers and their cousins, the quaternions. Okay, so this is where I'll stop today. And I'll try to get both of these lectures out tonight for